Now that we have the homogeneous solution to the equation x prime plus ax equals f of t, we need to look at the particular solution. However, it turns out we are in luck because every problem that we're going to be solving here is going to be having a DC voltage or DC current source, which means that's going to be constant, and that's going to turn out to make the f of t function constant. And if you remember learning about method of undetermined coefficients from 252, then that means you guess a constant as your particular solution, and you get something that looks like this. And so we're going to instead just change up the letters, what they're called, and we're going to call it this. And what it tells you is that every single first order circuit that we're solving in this chapter is going to look like this. It's going to be some constant plus a different constant, e to the negative t, divided by a third constant. And so instead of having to actually use calculus and solve a differential equation, in chapter 7 we're not going to do any of that. We're just going to ask you to find these three constants. And so K1, first off, that's going to be what happens as t goes to infinity. That's going to be the steady state solution. We're going to have this K2, which we're calling an amplitude factor. Basically, we're going to look at our initial and final conditions and use those to find out what it is. And then finally, we're going to have our time constant, our Greek letter tau here, and that's going to tell you how fast your exponential will grow or decay. So if you look at this graph right here, on this one we have t is 4 seconds, and you can see it only gradually decays. It takes longer and slower to decay. Whereas if you have a smaller time constant, it decays faster. And so we need to find these three constants, and once we have them, we can write down our answer, and that's how we're going to solve chapter 7 problems. So I'm going to show you with examples how do we find these three things.